Very good morning to you all. So we are in the second lecture of U224. Last week, when we started the course, we talked about computer abstractions. That was the first lecture. There we talked about how what are the different levels of abstractions that we have defined hardware as well as software when it comes to computer architecture, and we also talked about the interactions between these different abstractions and their meanings. So today, we are going to talk about some technology trends around computer architecture. So that involves a little bit of history about how we came to be in the current position when it comes to computer architecture and the related technologies. So as you guys are aware, the computer technology is changing really quickly compared to other technologies, and over the last several decades, we have seen a lot of different changes. So we are going to talk about some key changes in technology there to understand how we arrived at the current position in the history. So that it is very important to understand the history if we want to decide the future, right? So, and then we are going to talk a little bit about something called the power wall and also multiprocessors. And we will also talk about what is going to happen to your program once you write, compile, and deploy it on a computer. Underneath the covers, under the hood, what is going to happen? That is, those are the topics that we're going to cover today. Performance, we will be covering on. Okay, so before we get into the details, can you guys let me know if I'm audible and if everyone can see the screen? Hello. Okay. So, in order to talk about the history of computers, there's something that we sort of need to understand, which is called the Moore's law. A lot of hardware technology related to computer architecture is very much dependent or developed based around this thing called the Moore's law. Have you guys heard about this? Anyone here who is familiar with the name Moore's law? Come on, speak up. Yeah. Are you talking? Am I not hearing you? Can someone speak up? I feel like I'm talking to a wall.
Yes, sir, you're audible.
Right. So can someone tell me who is this fellow in the first place? Gordon Moore? Anyone familiar with the name? Who is it?
So am I audible?
Yeah.
So is that the same person who introduced the Moore model
Can you say that again? I didn't hear it properly.
Is it the same person that introduced the Moore model that we learned in?
I'm not actually sure about that. Let's have a look. Who introduced Moore? I don't think so, but let's verify. An interesting question. Okay, so no, not the same person. So, right, yes, Hirush typed something in the chat. Yes, co-founder of Intel. You guys know Intel, right? Intel is so still is, I guess, but used to be the biggest company in computer chips. I don't think Intel is the biggest anymore. We'll talk about these things as we go deep into the content. But yeah, so Gordon Moore was one of the co-founders of Intel. And Intel used to be one of the biggest companies which manufactures computer chips, computer processors. So even to date, I think most of the computer processors that we have inside computer processors, inside personal computers, so even most of the high performance, high-end servers are still being made by Intel. So yeah, Gordon Moore was one of the co-founders of that company, and then this person had put forth something called Moore's law. He said something, outlined something which the industry and everyone refer to as the Moore's law. Have you guys heard about what this Moore's law is? Anyone?
I think it was computation power doubles every couple of years or 3 years. I don't exactly remember the time period, but it's been observed that this trend has like started in the 1950s or something, and it's continues to hold even up to now.
Yes, exactly. Yeah, very good, Akiba. So what Moore's law states is, in essence, what it says is the number of transistors that you can put onto a standard computer chip will be doubled every 2 years. So that essentially translates into what you say, the amount of processing power, the computational power in a standard computer chips can double every year, which is a bit of a tricky translation, but we will get into those details as we go. We don't need to attack it right now, but generally what this person said was that, right? So the amount of transistors that we can put onto a computer chip will double every 2 years. It is not a law, right? It's not a law as, say, the law of gravity or something. It's more like a prediction. So this prediction took into account the demand for computational power that would happen in the future, that would increase in the future, right? So based on the demand, the industry would have to double every 2 years, double the amount of computational power that we can extract from a computer chip, processor chip. So that was the rough idea of this so-called Gordon-Moore's law. So whether the number of transistors is proportional to the amount of computational power, all these stuff we will have to understand. We will understand in due course, but the general idea was this. Okay, so what this this increase in computational power or the increase in the number of transistors on a computer chip made a lot of things possible, right? So compared to some several decades ago, we see some really new novel applications in applications of computers everywhere. A long time ago, several decades ago, computers were something of a specialty to perform, scientific calculations faster than a human can do. So computers used to be these massive machines that fills entire buildings. But the changes that we have seen so far throughout the history has enabled computers to become much smaller, but offer a lot more computational power. Because of that, computers are now ending up in all kinds of different places. Like, if you take a car, an automobile, you will find hundreds of computer processors in there, a modern car. And if you take, say, mobile phones, they are like all over the place, right? So becoming very commonly used instrument. But say 20 years ago, these were rarities. Mobile phones were a rarity and mostly used to make calls and messages. But now nearly every person has one, and there are so many things you can do with a mobile phone, right? So computer processors are there underneath those abilities. Then there are some other massively complex things like decoding the human genome, for example, which need immense power, immense computational power even today. So such massive tasks were possible because of improvements in computer architecture, which were based on these improvements in computer technology outlined by the Moore's law. So now, actually, right now, in the state of the art, these things like decoding human genome, we are even moving towards getting mobile devices to do such things. But these are still difficult problems, but we are even going towards that. So other things like the World Wide Web, the internet, basically, is possible because of these improvements. Search engines like Google or whatnot, which will tell you what you need to know, the answers to your questions in a matter of milliseconds. You just have to type something, and yeah, Google will figure out exactly what you need and give you really good interest from the internet. So such massive computational capabilities are possible today because of the path computer technology took in the history. So yeah, we can go ahead and say computers are pervasive, they're everywhere, and they can't be avoided, and in the future, of course, they will even spread even more. So our interest is in the technology which underpinned these developments in computer architecture. So let's have a look at this chart. So this chart shows the scaling of technology, how technology scaled or improved over the years. So this is from 1970 to 2010. And this chart shows some processor models made by Intel, Gordon Moore's company, within this period. Right. So the vertical axis shows the number of transistors in these chips, right? So at the bottom you can see 10 to the power 5, 10 to the power 6, that is a million transistors. 10 to the power 7 and so on, and 10 to the power 9 means a billion transistors, and it continues, right? So the horizontal axis is time from 1970 to 2010. So these two dotted lines that you can see, the bluish one shows the number of transistors in a computer chip doubling every 18 months, 1.5 years, right? If the number of transistors doubled every 18 months, that is the line that the chip should follow. The red one, reddish brown one, is representing the number of transistors doubling every 24 months, like Gordon Moore predicted, right? And you can see if you take real processor models, so these bars represent real processor models made by Intel and the number of transistors in those chips. So you can see that there's a close relationship between the actual number of transistors in these mainstream models with the doubling per 2 years curve, right? It's nearly perfectly following that curve. So this is not just because more Intel company wanted to make more happy and followed that. It is based on the demand for computational power and what was possible with technology. So even if you take other companies which appeared around this period, like AMD, another processor manufacturers, you will see the same pattern. So anyone familiar with the processor models that are on this chip? Oh, sorry, on this chart, sorry. So it starts with 4004, 8008, 8080, 8086. So around the time we get to 84, 86, you can see we are passing 1 million transistors inside the chip, right? The million transistors mark. We are passing around 84, 86 in 1989. So have you guys heard about these processor chips? I'm sure like you guys were born in when? 2000? 99-ish, somewhere around that, right? So yeah, so most of these are before your time, so to speak. But anyone familiar with these names? 80, 86, 84, 86, Pentium, Titanium. Have you guys heard about this? Yeah? No? Okay, let me ask a question this way. You know that the computer instruction set architecture in most Intel and they say even AMD processors, general purpose processors is called x86, right? It's the family of computer architectures, x86. Can you make a guess which of these processor models first started that architecture? First started or first was developed based on the x86 architecture? Can you make a guess? What's the first x86 processor? Make a guess. It's okay to be wrong. That was first x86, but might have been the first x86 processor. announced in the chat. Yes, yes. 8086, yeah. As you can imagine from the model, 8086 is the both the first mainstream processor based on the x86 architecture. x86 architecture has improved a lot since then. It's a family of instruction sets right now, but from there onwards, all of these processors are based on that architecture. So 86, 82, 86, 83, 86, 486, and so on. Even Pentium, all these other model names still use the x86 architecture. Nowadays, I think what we have what other model names we have? Core i7, Core i9, and whatnot. Yeah. So I remember the first computer that I used had a 8386 processor, some 16 megahertz clock speed or something. So that was around 1993, I think, if I remember correctly. The 83, 86, the 386 computers first arrived in the market around 1985. But here in Sri Lanka, those were rare things. Took some time to arrive here. Yeah, so around 1993 was when I first used the 386 computer. Back then, there were no graphical user interfaces, no GUIs. There was a black screen where you can type text. The operating system was called DOS, disk operating system back then, Microsoft operating system. There are other stuff, but the same thing. You only had a console there. That's it. Yeah, I don't know anything from there. Later on, in the 90s, between 1990 and 2000, the graphical user interfaces started to arrive in operating systems like Windows 95 and so on. Yeah. So that's a bit of history for you. So yeah, the processors we have here seemingly followed the Moore's law, and the number of transistors in these chips kept doubling, right? In around between 1985 and 1990, the number of transistors crossed the 1 million boundary, and around say 2008ish, it crossed the 1 billion boundary with these quad-core processors. Okay, so this happened. What do you think made this possible? This seemingly exponential increase in the number of transistors in a standard computer chip. It seems exponential, right? So what made this possible? How come we were able to increase these numbers, the number of transistors? What made it possible? What do you think? What do you think? So we have this technology to take a piece of silicon, a wafer of silicon, and etch transistors onto this, right? The process is called lithography. So somehow, over the time, we were able to add more and more transistors onto a standard computer chip. What made this possible? would say nanotechnology, not really. That comes a little later and not directly related. But the general idea, the way you're thinking is correct. Actually, what gave the room for improvement? Cost reduction. Cost reduction of producing the chip. Yes, true. But that is not the main reason why we were able to add more and more transistors. Cost reduction here, the cost to reduce. But what makes it possible for us to add these, for a very similar, small example, say if we had say 100,000 transistors in an 8080 processor, when it comes to 8086, we had say what 500,000 transistors or something around that. So what made it possible for us to jam all these transistors into the chip? Yes, had the components getting smaller and smaller over time. Yeah, exactly. That's the correct answer. Because we were able to make transistors smaller, right? The size of a transistor that was in an 8080 chip was much bigger compared to the size of a transistor, let's say, in a Pentium chip. So yeah, we were able to improve the lithography process so that we can make smaller transistors. Lithography is the process where you etch the semiconductor components onto the silicon. So yeah, we were able to make smaller transistors. That is the correct answer. So in the industry, if you're familiar, we refer to a number called feature size, measured by nanometers, right? So in 2004, we say the production process was a 90 nanometer manufacturing process. 2006, around 2006, we transferred into 65 nanometer process, manufacturing process. 2008, we had 45 nanometer manufacturing process, which was there for, it was a very famous process because a lot of things happened around that time, 2008, we talk about it. 32 nanometer, 22 nanometer, and anyone know the feature size that we have currently in modern chips right now around this time, these years? What's the size? Yes, Sigma, 7 nanometer and 5. Yeah, 5 nanometer, 7 nanometer. And we are talking about 3 nanometer, 2 nanometer, and 1 nanometer technology, right? So what is this number exactly? What does it refer to, feature size? Before I ask that question, let me just explain what this title is: Technology Scaling Roadmap. So this is, of course, how the technology scaled, the feature size scaled down over time, and this roadmap is produced by an entity called ITRX. ITRX stands for, if I remember correctly, International Technology Roadmap for Semiconductors. If I remember correctly, yeah. So that was an organization set up around 2001, and they predicted, based on the demand for computational power and the available technology and the potential improvements in technology, how the feature size scaling down would happen in the next 10 years to come. So this entity kept predicting or producing this roadmap for a number of years, and it doesn't exist anymore. It was dissolved in around 2015. Why? We'll talk about that in a little bit. But at the early part of the years 2000s, ITRA, this is what it predicted for the roadmap. 2004, 90 nanometer, 2006, 65 nanometer, 2008, 45, and so on, right? So, any idea what exactly is referred to by this feature? That nanometer is a distance measure, of course. Yeah. What does it refer to? What is this feature size? Any guesses? Make a guess, it's all right to be wrong. You're all here to learn. What do you think feature size is? Any guesses? Feature size in the manufacturing process. Reaction say the minimum distance between the source and drain. Yeah, yep. So yes, while I say yes, there's no hard set definition for the feature size. It usually the manufacturers use this or used this minimum distance between source and drain of a transistor, but it's more of a marketing term now rather than an actual definition, actual physical definition of the distance. So yeah, before we get into the detail, just let me point out a couple of fun facts about this 45 nanometer technology. With 45 nanometer feature size, you could fit the 30 million transistors into the head of a little pin, right? So you can imagine how tiny a distance we are talking about here. And you could fit more than 2000 across the width of a human hair. Just some fun facts to point out how tiny a thing we are talking, right? Compared to, let's say, 40 years back or 50 years back, earlier than this, when transistors first conceived. So these things are tiny. Okay, so this is just a diagram of a transistor etched on a silicon wafer, right? So this is a silicon substrate, and you have two metal contacts on either side, the gray pins on either side. So the minimum distance between the two metal contacts is referred to as the pitch. Half pitch is obviously half that. So sometimes manufacturers use this half pitch as the definition for feature size, but most commonly they use this distance shown here, the distance between the drain and source of the transistor, or the width of the channel, width of the gate. So they use that as the feature size, that distance. So this feature size sometimes you see in technical document, you see it called as the half pitch. Sometimes you see it called as the gate size or the channel width. So different measures are used for this, but essentially it's a measure which refers to the size of the transistor, right? So The smaller the transistor, the smaller that measure is. That is the idea. So we need to know that there is no hard and fast definition saying, okay, this is the exact thing measured by this nanometer number, right? It's an overall measure of the size of the transistor. Okay. So, okay, so with these improvements to the semiconductor manufacturing process, the lithography process, we can get smaller transistors, right? We were able to make smaller transistors and therefore have more transistors on the same chip as we kept improving the technology. So what does that mean? Does that mean better performance? Does having smaller transistors mean better performance? There has to be something connected, right? Because all these years, computers were able to offer more and more performance, more and more computational power. So there has to be some connection from making this transistor smaller to better performance. But how? Why it comes? Why is it like that? So one answer to that question is, with more and more transistors available on the chip, we can build more complex digital hardware, digital logic circuits, right? We can build complex functional units which can perform complex tasks, right? Say, for a very small example, say you had 100 transistors on a chip. With that, you can make some simple functional units. And to do complex tasks, you need to use the simple functional unit, the simple circuits, a number of times, right? If you want to break down a complex task into a number of smaller tasks, then you need to use these functional units, the simpler functional units, over and over again to do a series of simple operations to complete the overall complex operation, so something like that. So if you have more transistors, you have a lot more transistors on the chip, you could make a complex circuit which would do the complex operation in one go rather than break it down into small simple operations, a number of simple operations, right? So that is one way we could improve performance. We had a lot more transistors now on a chip all of a sudden, and with those transistors, we build more complex circuitry which can perform more complex tasks with the same time, right? So that is one way we could build complex hardware. Therefore, we could improve performance. The other way is, with the transistor being made smaller, that transistor could be operated with low voltage. The potential of electricity you would need to switch on this transistor, switch on and off this transistor, become low, right? Because the width of the channel becomes smaller, so the amount of push you need to operate that channel, operate the gate, is less, right? With less effort, you could operate the transistor. So therefore, you could switch it faster. You could switch it faster because the impedances of the internal dynamics of the transistor is lower now, right? So when we could switch the transistor on and off faster, that means the overall operation becomes faster, right? Overall time that is taken to perform an operation gets small, right? Okay, so now we kept improving performance like this. We kept improving the manufacturing process, which reduced the feature size over time and allowed us to gain better performance using the two ways that I say, right? So I think that now this is only up to the first chart at the top shows only up to 2012. What happened after that? From 2017 on. Now, in 2013, ITRS released the report, which is shown in this blue line, that in 2013, we would go from 22 nanometer technology to 20 nanometer technology. And by the time we reach 2015, it'll become 16 nanometer technology, I think. And we will keep going down like this. 12 nanometer, 7 nanometer, so 8, 7, and 5 nanometer by 2028. So where are we right now? So 2019, around say 12 nanometer manufacturing process, 12 nanometer feature size. 2023, 7 nanometer feature size. So, and we would, and they predicted that we would keep reducing the feature size even more, right? But clearly it shows the rate of reduction generally decreases, right? The rate of reduction in feature size generally decreases. That is what ITRS predicted. Then somehow all of a sudden in 2015, they in their last report in 2015 was the last report that ITRS produced. There they made some updates in. By the time we went to 2015, we were still around 25, 24 nanometer technology. We didn't go down to 16 as predicted, but there were some fast improvements to catch up with the original prediction by 2021, that is this year. Interestingly, to reach 10 nanometers, and then it would not change after that. They say we will stick with 10 nanometers after that. So what does this mean? Why was this sudden change of heart happened? There were a few things, but one of the most interesting things happened around this time, around 2015, was the manufacturing technology for semiconductors started a shift towards something called 3 digits, right? Before that, we were talking about a single layer. Now, in a diagram you showed, you saw earlier, how a transistor is etched in a silicon substrate, right? So the entire wafer, the substrate, contained a layer of such transistors. Every transistor on the same layer. The layer was one transistor thick, in other words. But around this time, 2013-15, this idea of 3D chips, where you have multiple layers of transistors on top of each other, became very popular suddenly. So that was one of the major reasons why this this change happened in the prediction, that the feature size would not reduce beyond 10 nanometers. And also, in 2015, this ITRS was dissolved. It is no more. They stopped making these predictions, but because a number of reasons. One is this, that the improvement in technology took a different turn, that you're not simply reducing the size of the transistor anymore, but to get the same effect, you do a number of different things. So still, the number of transistors that you could put into a chip kept improving, kept doubling, even following the Moore's law, but it was not exactly because the actual size of the transistor became small, but more due to other facts, like we were able to stack more transistors on top of each other with these 3 digits and so on. So, right. So, yeah. But the amount of transistors, the number of transistors on a regular standard computer chip kept increasing, and it still does. So the performance kept increasing because we were able to build more complex things, put more circuitry onto the chip, as well as we were able to switch the transistors faster and faster. Okay. Now, switching the transistors faster and faster, meaning the clock rate, we were able to improve, right, over the time. Clock is basically the switching of the transistors, right? How fast the transistors can switch from one state to the other. That is essentially what decides the clock rate, and it is dependent on other factors as well, but that the key factor is that. So as you can see, with the increasing number of transistors or the decreasing size of a transistor from around say 1980s up to early 2000s, we kept exponentially, we were able to increase the clock rate of the processor, of the chip, right? We were able to switch the transistors on and off fast. But around this time, early 2000s, 2001 to say 2007-ish, it took a turn the other side, other way around, right? The exponential increase slowed down and it started to reach a peak and settle at a point. Why do you think this happened? If what I said earlier was true, with smaller transistors, we are able to operate them with low voltages and we are able to switch them on and off faster. And you saw that even around this time, 2004, 7, and even beyond, we were able to make the transistors smaller. That argument changed beyond 2013, 15-ish. But before that, we were able to make the transistors smaller and therefore fit more transistors onto the chip. But we were not able to keep increasing the clock rate the same way. Why do you think that is? I didn't say that properly. Can you say that again? I haven't say they may have focused on efficiency. It's kind of correct. It does have something to do with efficiency, but efficiency is a broad term. No? Why were we not able to keep increasing the clock rate, even though the transistors kept getting smaller and smaller? Say, in metaphorical terms, that we hit a power wall, or the clock frequency hit a power wall. The clock frequency kept going upwards, kept increasing the rate that it grew upwards, but somehow it hit a wall, right? So this yellow thing here is the wall. It hit a wall and it had to turn. So what is this power wall? What has it to do with the clock frequency and the size of the transistors around? Sadia says, because there is a limit to how low the function voltage can be. Yes, that also played a factor. Yes. You need to distinctly recognize the different levels, right? Logic levels here. What is high, what is low. So we need to keep that distance as well. That was also a factor. But before that became a factor, this thing called the power wall became a factor which stopped the increase or slowed down the increase in clock rate. So what is this? What is the power wall? We'll talk about that. Right. So what do we have in this graph? In the horizontal axis, as usual, we have time or the models of mainstream processors released in these years, right? So horizontal axis is basically time. We have two vertical axes. The first one is clock rate of the processor, of the model processor that we have. And the other one is the power, the number of watts, power consumption in watts. Right. So as you can see, we kept increasing the number of transistors, decreasing the size of transistors. With that, we kept increasing the rate of switching the transistors. That is the clock rate, right? The clock rate, say for a 286 processor in 1982 was 12.5 megahertz. And a 386 processor around 1985 was 16 megahertz, right? So as I told you earlier, the first computer that I used it had a clock rate about 16 megahertz. And imagine how slow it could have been. Then here, this kept increasing 25 megahertz, 66 megahertz, 200 megahertz. So we are in the Pentium era now. And all of a sudden, right, we are in the Pentium 4 era around early, say 2001. We hit 2 gigahertz. And around 2004, we hit the 3600 megahertz, 3.6 gigahertz was the frequency, right? We were able to switch these transistors really, really fast. And with that, the power consumption also increases. The power required for the chip is also increased, right? Because we are switching the transistors on and off faster, the amount of energy you need per unit time kept increasing, right? The time required to switch the transistor kept getting smaller and smaller. So per second, the amount of power you need is more, even though the effort or the amount of energy you need to make a single switch is slower, you can do so many switches per second that the amount of power required by the chip becomes higher, right? Simple logic. So at around the Pentium 4 era, we required even more than 100 watts per chip, right? The Pentium 4 Prescott architecture, that chip required more than 100 watts to operate. So what's the issue here now? Yeah, okay, the chip needs power. And okay, we somehow provide power. What is the issue? We make better power supplies to provide this power to the chip. 100 watts, so even megawatt is the kilowatts or megawatts can be not supplied to the chip. What is the issue here? Thermal, exactly, Hariharan. Yeah, the thermal issue is it's the main thing, right? So yes, you can keep switching on these transistors on and off. You have a lot of these transistors on the chip, and you keep switching them on and off, all of these transistors, and that generates heat, right? The electrons travel through the semiconductors. The current is manipulated at different points inside the transistor or over the circuit, and all this current flowing throughout the chip generate heat. That was the issue. We were not able to cool the chips as fast as the chip keeps getting heated. So yeah, so that became the issue. And around that time, there were sort of an understanding in the industry that, as a rule of thumb, the maximum power that we would supply to a chip would stick at 100 megahertz. We would not cross that boundary. So because of these thermal issues, because the chip kept heating up, and of course, burning out. So because of that, the rule of thumb appeared in the industry saying, okay, we are limiting the maximum power that we are supplying to the chip to 100 watts, and we will live with that. We will somehow improve performance using some other methods. Right, I hope these arguments are clear. Okay, so this is the relationship between dynamic power to all the other factors like frequency, voltage, and capacitive load. So power required by a transistor chip, there are two parts. One is dynamic, one is static. Static refers to the power, the leakage power that is continually happening. Dynamic power refers to the power needed to switch the transistors on and off, right? So there are three factors in that equation. One is the capacitive load. Capacitive load is sort of an inherent constant to the transistor, which is based on the underlying substrate, right? Properties of silicon or whatever the semiconductor that was used, and the properties of the structure of the transistor itself, right? How the transistor was constructed. So yeah, that is a constant. We can take that as constant. The other variable factors are the voltage, right? The voltage applied to the transistor, and then the frequency, how fast are we trying to switch these transistors on and off. So yeah, if you say compare the 8286 processor with the top one here, Pentium 4, you can see the frequency difference in frequency is around 300 times, right? This is roughly 12, and this is 3600. So the frequency, the difference in frequency is about 300-fold here, and the difference in voltage to switch the transistor, what is the voltage used? The difference is here the voltage goes around, the maximum voltage is around 5 volts, and here in Pentium 4 it goes around 1 volt. So yeah, so there was a reduction, right, from 5 to 1, and the factor is of order 2 here. So the reduction was of magnitude roughly 25 times, right? Or rather 5 to 1, 25 times. So the voltage factor was a reduction of 25 times. The other one, the frequency factor, was an increase in 300 times. So that is why the dynamic power kept increasing. So that is just to give you the idea how the power kept increasing, but we went beyond that, right? So the power itself is not just the issue; the heat was the issue. So some interesting things happened around that time, around this 2004 era. People tried to come up with various cooling methods for computer chips, using fans, using say liquid-based cooling, like in cars, right? You put radiators with a liquid flowing through them to draw the heat out. So a lot of different things appeared around that time, trying to overcome this issue, right? But it did not succeed, obviously, because we hit that wall and we had to look for other options. Then some interesting term appeared around that time in the market called overclocking. Anyone here who had done overclocking in their computer processes? Then gamers here, you might still even do. Anyone here who has tried overclocking the computer processor? Overclocking is using a clock speed higher than what is recommended, basically. Anyone who has tried something like that? The previous year, there were a couple of people every time. When okay, Harihara, months, right? What happened? Did you manage to get it done safely, or did you manage to fry your computer?
No, sir, like too much heat. It was released. My processor was not good that much time. I tried to play a game, then I tried to overclock it, but it was not that much successful.
Okay, yeah. So yeah, that kept happening around that time. So like you see in this chart, the chart says 3600 megahertz for Pentium 4 Prescott processor around 2004, right? But what the manufacturers, Intel and other manufacturers, what they did was they did a little marketing gimmick. They said this processor is limited to say 3600 megahertz, but you can overclock it up to say even I remember there are processors marketed saying it could go up to 4100 megahertz around this time, Pentium 4. So what they say is, okay, we can let you use a higher clock, but it's on you, right? We are not going to provide any guarantees. We are saying, okay, use 3600 clock, the standard one, and it will be safe for the processor. If you want to, you can keep increasing even more to get better performance, right? So that's what they did. It was a marketing gimmick, and it was very attractive to people like gamers who wanted to extract a little bit more power from their CPU, power intensive tasks. But what happened, obviously, you use a higher frequency, it generated more heat, and there was a good chance that you're going to burn the process out, you're going to fry the process. So, and it did happen. I also had done overclocking, but thankfully hadn't fried the processor. But yeah, so that was a thing back then, overclocking, especially targeting gamers. Okay, so I hope the idea is clear, right? Why this increase stopped? Why this increase in clock frequency stopped? So does that mean we were not able to keep improving the amount of computation power in the processor? Obviously not, right? We did improve the power in computer processor. We had to look for other ways to do this. So this challenge in power forced the manufacturers and the broader computing industry to find other solutions, other ways to keep improving computational power in computers. So, but anyway, the perceived computational power increase in computers slowed down around this time from 2002-ish, as you can see, from 2002-ish here around this time, the perceived computational power, increase in perceived computational power slowed down. So it doesn't say the computer slowed down, computer kept increasing the perceived power in a computer, but the increase slowed down around that time. So what happened after that was there was a large shift by manufacturers from putting a single processor in a chip to putting multiple processors on the chip, right, in the same chip. So basically, the problem was we have more and more transistors on the chip. We still keep getting more and more transistors on the chip, but we can't use all these transistors at the same time because the chip keeps getting heating up, right? So what to do with these transistors? How to use these transistors? We can't make really complex logic, say, circuits. But one was obviously making more complex logic circuit, but there was a limit to that as well, which we'll talk about in a second. So we had to come up with ways to cleverly utilize what's on the chip, right? The transistors on the chip. Now, these are some processors that entered the market around this time, where these are different manufacturers, and you can see the number of processor cores or processors on the same chip. They try to keep increasing, right? So this AMD Barcelona chip, it had 4 cores, 4 processors. Intel also had multiple processors. IBM also had multiple processors, and other manufacturers, right? Even 8 processors per chip. So the power also, you can see the relevant numbers for these chips, right? So there was a general shift from single core processors to multi-core processors, multiple processors on the same chip. What is the idea behind that? To keep increasing the perceived power, perceived computational power, because of some other limitation, right? Other than the power heat thing, okay, we come up with, we hit a wall, we have a limitation, that is fine. But there was something else which stopped us from making more and more complex circuits using the available transistors. Because of that thing, we will talk about that thing in a little bit. We tried to increase the number of processors that we put onto the chip using these transistors. And the assumption was based on, if you put more processors on the chip, of course, we can get more work done. And like that, we can keep improving the perceived processing power. The perceived power that a user would see in a computer, right? So if we went by that, the plan was to double the number of cores per chip per generation, right? Roughly every 2 years, right? That is, again, following the Moore's law, right? Moore's law says you have double the number of transistors every 2 years. With those transistors, we can double the number of processor cores per chip every 2 years. But did that happen? Do we have that many processors on chips right now? So this goes around, what, 2006, right? 2006, we had, say, okay, on average, 4 processors on the chip, let's say. Then, if we went by this 2008, we would have had 8 in general standard chips. Then 2010, 16 processors on a chip. Likewise, we should have hundreds of processors on the chip by now, right? Do we have that? Do we have that many processors or processor cores in a single chip? We don't, right? It didn't happen. Why didn't it happen? It didn't happen as predicted or as expected. That's what we are going to talk about right now. So, multi-core processors or multi-processors basically they mean you have more than one processor per chip, right? Okay. So, how to make use of these processors? You need explicitly parallel programming, meaning the programmer, the person who writes the program, needs to write that program understanding that there are multiple processes. So I'm writing this program as, say, there are four processes. I'm writing this program as 4 programs which collaborate together to get the work done. Have you guys done parallel programming? Say using thread packages in C. Have you guys done that? Like in C, there's a package called pthreads, and there are other packages as well for you to write programs which have multiple threads or multiple processes. You can have communication between these processes as well, synchronization between processes. Have you guys done it? Are you familiar with threaded programming, multi-threading, multi-threaded programming? No? Okay, so that's fine. You don't have just for to satisfy your curiosity, try it. There are plenty of examples on the internet. Go and have a look. Nearly all the programming languages have this concept of multiple threads or parallel processes. In C, I would suggest you try C. In C, you can use a package called pthreads to branch your program into multiple threads or processes. So these can be treated as separate sequences of execution. So you can put each thread on a separate processor and have them run at the same time. So anyway, so the idea was the programmer needed to use these parallel programming techniques explicitly or else manually when the programs are written. That means the compiler and operating system and other infrastructure which are there, the system level infrastructure, also needed to provide this functionality, support this functionality. So this different from something called instruction level parallelism. Right? You will be learning this in the next topics, next chapters in this course. So instruction level parallelism is it refers to something called let's put it like this. Now, when your program is converted into an assembly program, right? When your C program is compiled into an assembly sequence, it's a sequence of instructions, right? The processor will fetch one instruction and execute it, then fetch the next instruction and execute it, right? Sequentially, one after the other, it happens like that. So there are techniques where we can bring multiple instructions into the CPU at the same time and try to execute it. You can't do this all the time, but sometimes there are opportunities for the processor to do this. And such techniques are referred to as instruction level parallelism. Those are entirely hardware-based solutions. So the hardware, the circuitry itself is designed like that, and the compiler will support it. But the programmer doesn't need to be too concerned about this, right? It's hidden from the program. You can write a program. I can write a program in C and not worry how the hardware will run some of these instructions in parallel. The hardware will handle it, right? Those techniques are called ILP or instruction level parallelism. But to make use of multiple processors on the same chip, we need explicit parallel programming, right? Okay. I hope that distinction is clear. So this explicit parallel programming is hard to do from a programmer's perspective, right? The programmers would need to have a really good understanding about the hardware, the processor chips architecture, and they would need some very specific constructs at programming level to get this done, to do this, right? So, but this is done, and this is something that you also should be able to do as computer engineers before you graduate, because when you program for performance, when you write massive computational programs where performance is critical, where you need to extract the best performance from the system, you need to understand the hardware and you need to do explicit parallel programming. You would need to think about things like balancing the load between threads, right? Between different processes. Balancing the load between the processors so that every processor is doing a decent amount of work all the time. That you are not letting one processor sit idle while another processor is pulling most of the work, right? So load balancing the program needs to be aware of, and optimizing communication and synchronization, right? if the application is broken down into multiple processes, each running on a separate hardware processor core, the communication between these processor cores and the synchronization between the programs or parts of programs running on the processors is very important, right? One thread should not keep eternally waiting for another thread to supply a piece of data, right? You should synchronize the programs in such a way that the maximum performance is extracted from the system. Otherwise, you are not using the available hardware to the best effect. So yeah, so it's hard thing to do, not impossible, hard thing to do, and you should be able to do as computer engineers. So, but a general, a regular programmer, for a regular programmer, it was too much. It is too much. So, yeah, that is the sort of the problems brought by multi-core processors into the computer programming domain. Okay, right. The next thing we want to talk about is what happens to your program. What happens once you write a C program, let's say, and compile it and run it, what happens? Right. So a computer system, we can split it into three main domains. If you remember from the original picture that we talked about last week, that also has these components, right? We have the hardware domain, hardware layer, and around that we have the systems layer. Systems layer, here we have defined as software. That includes things like compilers, operating system, and so on. Then the outermost layer is application software. These are the programs that programmers write. Okay, so a computer system can be sort of at a very crude level broken down into these three layers. Application software are written in high-level languages like, say, C or Java or R or Python or whatnot. There are so many hundreds and thousands of high-level languages, each optimized for some specific types of programs, specific types of applications, right? So for machine learning type applications, you have different types of programming languages which are optimized for those applications. For more systems-oriented programs, you have things like C. C is relatively lower level compared to, say, R or Python. Then, yeah, so you have all kinds of different applications of that written using different high-level languages. Right. Then the system software layer includes the tool chain which supports these programming languages like compilers which understand the programming language as well as the underlying hardware, computer architecture inside this. Then you have assemblers which will translate your assembly program into machine code. Then yeah, the compiler, assembler plus linker, those chain of tools will let you translate your high-level program, high-level code into machine code. Then other than that, you have operating system. These are like service software. Why do you have them? Because we don't trust application level software, right? We can't always trust. People can write programs, do anything, right? These things can be malicious as well. And these things also don't take into account what other programs, right? You can write a program and I can write a program, and we will never think about what, I will never think about what your program is going to do. So there may be overlaps, collisions about what we are trying to do if we try to run both programs on the same system. So that is why the operating system comes into the picture. It's a service program, collection of service programs which are managing resources, handling inputs and outputs, managing things like memory, storage, and other hardware resources, and handle things like scheduling tasks, so scheduling threads, sharing resources between programs, right? So all these services are provided by the operating system. For example, do you ever worry about the say where your program goes into the memory, or where your local variables are placed in the memory? Do you ever worry when you write the program? You don't, right? Because the operating system takes care of those things. Operating system doesn't allow you to handle all the hardware by yourself. Operating system will do those for you, for your program, right? So the operating system will guarantee that you're not breaking the hardware, you're not breaking the rules set by the hardware. So that level of abstraction is provided by the operating system. Those are the main system software components. Then underneath that, you have hardware. You have the processor, the architecture, microarchitecture, connected with memory. You might have a hierarchy of memory with, say, caches, multiple levels of caches, and so on. If you are not familiar with these terms I'm using, don't worry, you will learn. We will learn all details about these things in this course, right? Cache memory, level 1 cache, level 2 cache, level 3 cache, then main memory, input-output controllers, all these things, all the hardware, actual hardware, the controllers are there in the middle of all this. The system software hides all these hardware stuff from the programmers, so the programmers can have an easier time writing the programs or the applications. Okay, so this is the system we are talking about, and this is the level that your program goes through in this system, right? So at the very high level, the high level languages that you have, we are taking this, taking C as an example here. So this high level, at the highest level, the representation of your program is closer to the problem domain, right? Closer to the problem and the algorithmic solution. The program is basically a representation of your algorithm, right? Algorithm is a solution to the problem. So we keep these high-level languages closer to the problem domain, so it is easy and productive for programmers to work with. Yeah, so in this example here, what we have here, we have a function to swap two values in an array, right? The array is pointed to by this v pointer. It's the pointer at the start of the array. Then we have another input to the function called k, that is the position from which we need to do the swap. So what do we do in this little function here? We have a temporary variable and integer. We take the kth position, the value from the kth position in this array, and put it in the temporary variable, and we move the next value after that position to the kth position and put the temporary kth position's value, which is in the temporary variable, to the k+1 position. A very simple swap procedure, right? Swapping two values in an array. So this is something that you would have done hundreds and thousands of times in your programs, right? A very simple procedure. So, okay, you write this in C language, high-level language. You take the GCC compiler or a different C compiler and ask it to convert this into an assembly program, right? What happens? Compiler throws something like this as the output. What do we have here? These are instructions. The instructions are coming from the instruction set, right? Different instructions in the instruction set, we get them. We try and represent the high-level program using a sequence of instructions. That is what the compiler does. So the output of the compiler is basically a textual representation of instructions, right? These are not ones and zeros. This is a textual representation. So we have how many instructions? 1, 2, 3, 4, 5, 6, 7 instructions to do this swap operation, so swap function, to implement the swap function. we have 7 instructions. So in the SOP function, we had 1, 2, 3, 4, 5 statements, including the function definition. Here we have 7 instructions to implement that using the instruction set. So what do we do here? You multiply the value in a register 5 with the immediate value number 4 and put the result in register number 2, right? Very similar to ARM instruction here. But this instruction set is not ARM. What we're using here is something called mix. It's a different instruction set. And but there are a lot of similarities between mix and ARM. Like, I asked you guys to have a look at the very first day. On the very first day, I hope some of you had a look at least. It will help you a lot to understand things much better. If you haven't done that, please go and do it. So here, what we have are instructions from the mix instruction set. So what do? We take from register number 5. Register number 5, is that anything specific? We try and multiply that with the value 4 and put it into a register number 2. So why is this? What do we do with that value afterwards? We take that value in register number 4, add it to the value in take the value in register number 2, add it to the value in register number 4, and store it in register number 2. So what are we trying to do here? So if you look at this carefully, what is happening here is you're taking the second variable here. This is the position. This is pointing to the position. This is indicating the position in the array, right? The position in the array, and the other one is the beginning position, the start position in the array. So those two are given in these 2 variables, right? So there must be some sort of a definition in the instruction set, a convention saying the arguments to the function should be passed through registers number 4 and 5, right? There must be some sort of a convention like that. So register number 4 is holding this first argument, and register number 5 is holding the second argument. So what we're doing here is taking k, multiplying it by 4, and putting it into some temporary register. And then we add the v value here, the beginning of the array value here to that point, right? So what are we essentially doing? We are trying to generate this value, right? We are trying to generate the address of the kth position in the array v, right? So why are we multiplying by 4? I'll let you figure that out. So essentially, the logic in the high-level language is broken down into these atomic operations which are given by the instruction set. So that is what the compiler does, right? Then you can go through and try and understand this. It's not difficult, actually. You can try and understand this. I'm not going to walk you through the entirety right now because you don't have time. So what happens after that? What does the assembler do? Assembler, it takes these instructions, the sequence of instructions, and do a one-to-one mapping into machine code, right? Into ones and zeros, binary. So if you look at the machine code, it also has 7 lines, 7 instructions, right? The same 7 instructions that you have here in the assembly code. So what the assembler does is simply replace these instructions with the corresponding ones and zeros defined by the instruction set. So here we have 32 bits in each instruction. If you take the first, so you can break this down, and some parts of this will refer to the operation, and other parts of this will refer to values, right? So here, for example, this value, immediate value 4, it's here, right? This is the immediate value number 4. Sorry, that's not it. My bad. Yeah. This one I get. Anyway, I can't remember the format of MIPS instruction set, but basically what you have here in the machine code is a composition of this instruction, right? Some pattern of ones and zeros somewhere here will say this instruction is multiply immediate. Then the rest of the ones and zeros, rest of the regions of ones and zeros will define the destination, the first operand and the second operand. You can figure that out looking at the MIPS instruction set. So anyway, so that is how your program is translated into machine language. So this is called a binary image, and this binary is taken and put into the memory, right? Somewhere specific in the memory, you go and put this. Then the CPU should be able to pull these instructions from the memory, bring one after the other, and execute, right? How does that happen? How does this execution happen under the kernel? So this is like a typical block diagram of a computer. You have your compiler and other interfaces which will translate your program into machine code, right? And then you put the machine code into somewhere in the memory, right here, right? The machine code is sent into the memory. It's stored somewhere in the memory. Actually, it's stored somewhere in a secondary storage, right? In your hard disk or some form of permanent storage. When you want to run it, you bring it into the memory. You bring it and put it somewhere in the memory. So these inputs might be coming from that secondary storage, or it might be coming from network even, right? So anyhow, the program, the ones and zeros are brought into the memory, and the CPU, what it will do is bring instruction by instruction, like on a conveyor belt in production line, bring instruction by instruction into the CPU and execute, right? Do what is said by that instruction. So inside the CPU, you have two different things. You have something called the data path, and you have something called the control. So the data path is basically the set or collection of logic circuits which form a path the instruction travels through the CPU. Right? The instruction goes from one logic circuit to the other logic circuit inside the CPU and finish the execution. So that the path of logic circuits is called the data path, and this control is basically another logic circuit which will govern the travel of these instructions and data through the data path. The control logic ensures the instructions and data travels through the data path in the appropriate way. Right? So those are the two main components that you have inside the CPU, control and data path. So these instructions are brought one by one into the data path by the control, and the control makes sure the instruction travels through the data path appropriately and gets executed appropriately, and certain results that might be generated when the instructions travel through the data path are sent back to the memory and stored. And sometimes some of these results might need to be sent into secondary storage or network or whatever other place, right? So yeah, inputs and outputs can mean some simple things like, say, displays, keyboards, mice, whatnot. Or more importantly, it can mean things like secondary storage, like hard disks or CDs, flash, and whatnot, and network adapters, right? Traveling through network in network adapters, network interfaces to other computers. Right, so that is basically, very simply saying, how under the hood of your computer, how it deals with the programs after the programs are compiled and when you want to run it. Right, so yeah, data path performs operation on data. The functional units perform operations on data and instruction. Control make sure that things happen according to the plan. The instructions and data travel through the data path accordingly. Then when it comes to memory, we have things called cache memory in the CPU, where the idea is getting things from the memory is a little slower. So you might want to keep, be able to store some information on the chip itself, on the CPU itself. So you could put some fast form of memory on the chip very close to the CPU. And that is, we refer to as cache memory. You will learn how this works and how to implement, and you will actually go and implement one yourself. Right. So those are the main components that you have in the CPU. So this is a very old model of CPU, AMD Barcelona, which had 4 processor cores, right? So this is the actual image of the chip. This is an enlarged magnified image. This actual size of the chip is much smaller. And this is the layout on the right hand side. You can see you have 4 processor cores. You can identify, right? You can identify the areas defining these 4 processor cores. So the first core here, so that those are the stuff that go into the first processor core in the chip. This is core number 2, and this is core number 3, and that is core number 4. So in each of these cores, you have a lot of different other things as well. So here inside here, if you can see this area, that is the floating point unit, which helps the CPU do floating point operations, right? If the numbers are stored in floating point format, this is the logic circuit that helps you do floating point addition, multiplication, division, things like that, right? Operations on floating point numbers. So that is the logic circuit, and it's a big component in the CPU core, right? So then you have here, you have a load store unit, which lets the CPU put things in the memory and print things from the memory, right? So the logic that handles those operations are here. And here you can find the rest of the execution other than floating point. The integer execution can be done in a smaller logic circuit here. Then this part of the CPU is about fetching and decoding instruction. So instruction, that is the 1s and 0s instructions stored in the memory, bringing the correct one into the CPU and making sense of those 1s and 0s. That is decoding. Making some sense of those 1s and 0s is done by the logic circuit here. And the rest of these things are more memory related. So this is a level 1 data cache. This is a level 1 instruction cache. Right? The instructions are brought into this and then fetched into the CPU through the fetch unit. So this particular cache memory stores only instructions, right? That is only parts of the program. This particular cache, level 1 data cache, stores data, right? Things like parts of images or parts of numbers stored in memory. So, and then you have a unified level 2 cache. Both data and instructions are here, can be stored here. So this is a common cache for data and instructions, and it's bigger, you can see. And it's further away from the execution fetch parts of the CPU. So the time to bring can be slower here as well. So the control for these level 2 cache is here, control logic for the level 2 cache circuit is here, and that forms one CPU core. And the other cores are also very similar to that. The layouts are identical, just mirror image. So what else do we have? We have in the middle here, we have something called the North Bridge. That is the main communication circuitry which lets the level 2 cache connect to the main memory, right? So North Bridge is the main communication circuitry which lets the CPUs connect to the main memory. And here you have something called the DDR PHI. PHI is the physical controller. DDR is dual data rate memory physical controller. So that lets through the North Bridge, the CPUs will reach the memory through the DDR controller. It has something to do with the design of memory as well. So we have some other physical controllers as well. HTE, hypertransport is some proprietary protocol for AMD back then. So different communication protocols for other I/O entities inside the computer, like say graphics cards or other plug-in cards that you can put inside the computer. Right. Okay. So that is the layout of this particular chip. You can go and have a look at a nice website called wikichip.org to have a better look into these things. Let me actually try and show that. Yes, this is the website wikichip.org. I'll ask you to go there and have a look. Just have a look by yourself. You'll have a lot of information here, right? So this Intel processor architectures based on x86, AMD processors based on x86 instruction set, ARM processors, based on ARM instruction set, and other processors like say Samsung processors that you have inside your Samsung phones. Based on the ARM architecture, right? A lot of different things you have, which are publicly available on the internet. Everything is sort of gathered here, right? About processors like OI3, i579, Xeon, AMD processors, Apple A series processors, Qualcomm processors, stuff that you find inside my smartphones these days. Snapdragon and whatnot, right? A lot of different things you can find. Have a look. And even things like these manufacturing process feature size descriptions, transistor types of transistors, stack. Here you can see towards the 5 nanometer, 3 nanometer, we have transistors stacked on top of each other. So we can just click on this and have more details. So right now, the mainstream thing is 10 and 7 nanometer technology, but in the next couple of years, we'll be shifting more towards 5 and 3 nanometer technology. So these right now, these numbers don't really mean the size of the gate anymore, size of the channel anymore. Right here, you can see the width of the channel is larger, and these are not in proportion, but the width of the channel is larger compared to the width of the channel in this 10 nanometer. But it's not the case anymore. We keep using smaller numbers, but the width of the channel is not changing that much. But other methods, other techniques allow us to put more transistors on the chip. So have a look here. You'll find interesting things. Things about what processors are made using what architectures. This 5 nanometer lithographic process right now, and in the industry, what are the processes that are used? So in 2023, we are expecting some Intel processors using say PE. These are the old names probably. Yeah. And some Samsung processors already use the 5 nanometer process. But yeah, you can have a look here. Right. So going back to our slide. Next is performance, which we will not start today. We'll do that on Friday. So before we start the class, are there any questions? There are no questions. We can stop for today.